Exercise 1824 is asking you to draw a major product of a Birch reduction. So let's talk about what a Birch reduction is. In general, in organic chemistry, when you have a reduction, you're creating more bonds to hydrogen. So fewer bonds to electronegative atoms and more bonds to hydrogen. Now in benzene, we're at the places where you have a lot of bonds is bonds between the carbons. So you're going to replace one of those bonds, the double bonds, the pi bonds between carbon, with bonds to hydrogens. Now the recipe, we'll just show the overall recipe and then we'll talk about how it's happening, is you have solid sodium and you usually mix that with methanol, CH3OH, and ammonia, NH3. And the final result that you get is you get just, instead of 3 pi bonds, you get 2. You've replaced the bonds between the carbons with bonds between the hydrogens, and the specific pattern here is that the pi bonds are on opposite ends of the ring. So that's what you get when you do a Birch reduction. Now, there are 2 variations to this. If you have a ring with a branch on it, it behaves just a little bit differently. If you have a ring with a branch that has an electron withdrawing group, for example, an electronegative atom, like a carbonyl, then when you do this same reaction, you only get reduction at one place. So the branch that has the electron withdrawing group, that carbon, that's always the one that gets the hydrogen. In other words, that's always the one that is not going to be in a pi bond. The pi bonds will always be next door. On the other hand, if you have an alkyl group, so any sort of carbon chain, here I'll just put a methyl group, and you do the same reaction, you still get the reduction, but the pi bond will always be bonded to the carbon that has that branch on it. So in other words, this carbon does not get reduced. It does not get a hydrogen. So when you look at this, you shouldn't be thinking, oh, okay, you always get 2 vertical lines. Because the molecule is rotating in space, you could draw those 2 pi bonds on opposite ends of the ring going in any orientation. If you don't have any branches on the benzene, it doesn't matter where you put them. If you have an electron withdrawing group, the electron withdrawing group is going to be on one of the ends that does not have the pi bonds. And if you have an electron donating group, like an alkyl group, then it will always be attached to one of the pi bonds. It'll always be attached to one of the pi bonds. So the carbon that gets the hydrogen will always be the one that's next door. So that's a pattern, but where is that coming from? Why is that happening? And why does this reaction even happen in the first place? So let's walk through the mechanism really quickly, and then hopefully you'll see why you're getting this pattern for when you have these electron withdrawing or electron donating branches, and hopefully that'll help you to remember this. So first you have, let me draw a benzene with all the hydrogens on it. Okay, and each of the carbons in benzene has 1 hydrogen on it. Remember, we're doing a reduction, so we're going to have a bond to a second hydrogen on a couple of these carbons. So there's our benzene ring, and the first thing we treat it with is the sodium. Now the sodium is usually in the presence of liquid ammonia, which activates it a little bit, and metals are kind of strange. You know of phases, you think of solids, liquids, and gases, and you think solids, liquids, and gases, and you think that metals, like sodium, are solids. And it's kind of like those little mind trick pictures, where you look at them one way and it's a rabbit, you look at the other way and it's a duck. If you look at it one way, I guess you could say that metals are solids. But the truth is, you can look at them another way, and they are a different type of matter, a different phase of matter called plasma. So you have 4 phases of matter: solid, liquid, gas, and plasma. Plasma is actually the most abundant phase of matter in the universe. A plasma is when you have protons, neutrons, or electrons all in a jumbled up soup. So they're not organized into atoms. They're all just sort of mixing with each other in a way that does not create atoms. So anytime you have subatomic particles not associated into atoms, that soup is called a plasma. And you've seen them in places. It's plasmas that cause the aurora borealis, it's plasmas that are responsible for static electricity, and the stars are so hot that the protons, neutrons, and electrons in them are too energetic to form atoms. They just knock against each other. So stars are made of plasma, which is why plasma is the most abundant phase in the universe. But you can also think of metals as plasma, because you have a bunch of nuclei in a metal, and the electrons are not just swirling around individual nuclei like you would expect in a small molecule. Instead, they're washing over in enormous tsunami-like waves. Hundreds of trillions of electrons are washing over and swirling in between and weaving in and out of each of these nuclei. The electrons in metals are not specifically associated with the nuclei, which is why metals conduct electricity so well, because an electron can travel from one end of the metal to the other end without getting stuck to one of the nuclei. Also, that should make sense, because metals are on the far left of the periodic table. They have really low electronegativity, which means that the nuclei don't hold on to electrons very well. They don't attract valence electrons very well. So these metals are like huge soups of disassociated electrons and nuclei, where the nuclei are like blueberries in a blueberry muffin. So, in other words, the big takeaway from that is it's very easy for a metal to lose electrons. And if you have a whole chunk of metal, it can lose just one electron and create radicals. And that's significant for this reaction because we're trying to react benzene itself. Benzene is not reactive. The only way we're going to get it to react is to react it with something that's really reactive, and that would be a radical, and something that has an unpaired electron. And because all of those electrons in sodium are disassociated from individual nuclei, it's easy for the big glob of sodium to lose an electron. And so that's what happens in this first step. It's a radical reaction. The sodium donates an electron to one of the carbons. And that would be very, very unstable. The pi bond that's there donates one of its electrons to that same carbon, so we're sort of passing the baton of the radical now. The other electron goes to the pi bond next door. And then you'd have a radical in between those two atoms, so that steals one electron from the pi bond there. So again, passing the baton of this radical, no one wants to keep it. Finally, the unpaired electron lands on the para position to where the the radical originally attacked. And so your first intermediate is to have this benzene ring. Notice this pi bond didn't go anywhere. We now have a pi bond here. We don't between those two carbons. On top, we're going to have a lone pair. So let me draw that hydrogen in. On top, we have a lone pair with that full negative charge. And on the bottom, we have a radical. So let me fill the other hydrogens in. All right. So there's our molecule. And now that we have a full lone pair here, now, and the reason why the pi bonds fractured or splintered in this way, in order to get the pi bond and the lone pairs on this exact position, is so that they could exist in parallel p orbitals that go all the way around the ring. So they're trying to stabilize themselves by delocalizing. So what we have here is a really good nucleophile. And so that's going to attack a hydrogen, and that's where the methanol comes in. So methanol is like that. The full negative charge in the lone pair attacks the hydrogen. It loses the electrons in the other bond. It's a typical proton transfer. So you end up getting this molecule. Notice the electrons are now in a bond, and we now have this hydrogen. So this is what's making this a reduction, more bonds to hydrogen. Here we have a new bond to hydrogen that we didn't have in our original molecule. So that's one, but we still have this really energetic radical, and that ends up taking another lone pair from the sodium. So that's moving around, knocks into sodium, and the sodium has plenty of electrons to give away. It loses electrons very easily. They're not even associated into atoms in the metal. So it donates one electron there, and you end up getting Suppose I could have drawn that. Let me just draw that to this one on top. So this is the same molecule, donating it there. And what you end up getting is a full lone pair there. And now that you have the full lone pair with a negative charge, a similar thing happens as happened in this first step, or that second step. Methanol comes in. The lone pair acts as a nucleophile, and you do a proton transfer. And so you've ended up adding two hydrogens on opposite sides of the ring. So I'll put them in blue here. You have the hydrogen you've added on top, hydrogen you've added on the bottom. And so you've reduced those two carbons. The carbons that aren't in pi bonds, those are the carbons that you've reduced. Okay, so that's the mechanism for how this happens on just a regular benzene. But what we want to know, what we want to explain, is why you would get this weird pattern with these branches. And for that, let me just zoom in on this first intermediate. Imagine if at this top carbon you didn't have a hydrogen, instead you had an electron withdrawing group. So let's say like an electronegative element, like oxygen there. Would that electron withdrawing group help to stabilize this negative charge that forms in the very beginning, or would it destabilize it? Well, because it's electronegative, it's pulling electron density towards itself and helping to spread out the electron density. So because it's withdrawing electron density, it helps to stabilize that negative charge, and so that the lone pair tends to form on the atom where the branch is. And notice that that lone pair ultimately turns into a hydrogen. So that's why when you have this electron withdrawing group, you end up putting the hydrogen on the same carbon that has the electron withdrawing group. On the other hand, let's say it wasn't an electron withdrawing group. Let's say it was an electron donating group, like a methyl group. any alkyl group. And just as a review, remember that if you have a p orbital on one atom, and next door you have an sp3 hybridized carbon, so like an alkyl group, there are going to be a few different sp3 orbitals. There will be a couple going down, there will be one going toward the bonds, those are your sp3 orbitals, and then there's going to be one kind of up and to the left in this case. Now, that one that's sort of going up doesn't overlap the best, but it does overlap a little bit with the p orbital. One of the lobes overlaps a little bit with the p orbital, and that's called hyperconjugation. It's not the best. It's definitely not the type of conjugation you get with two parallel p orbitals, but it's something. And so that's one of the ways that these alkyl groups donate electrons into a p orbital, through hyperconjugation. So if we have one of those sp3 hybridized carbons, and we have a p orbital here, you could see how one of those sp3 orbitals is going to donate electron density into that p orbital. So in this case, you're not withdrawing electrons, you're adding electrons in. Now you already have a lot of electrons there. And so if you add electrons in, that's going to really destabilize it. That will discourage this lone pair ever from forming on the carbon that has the alkyl group on it. And notice that lone pair turns into a hydrogen, and so you never get the hydrogen added on the carbon that has that electron donating alkyl group. The hydrogen gets added next door, but it never gets added to the carbon that has the electron donating group. So that explains these patterns. First, why this is happening. Second, why you always reduce the carbon that's bonded to an electron withdrawing group, and why you never reduce the carbon that's added to an electron donating group. So that being said, that long explanation hopefully will make this process much simpler, because they're not asking you to draw the mechanism. They're not even asking you to explain this. They're asking you to predict the product, predict the major product obtained when each of the following compounds is treated with Birch conditions. So that means we're treating them with sodium in methanol. So sodium's there to create the radicals, methanol's there to add the hydrogen, and ammonia, which activates the sodium. So that's what we're treating each one of these with, and the question is, what's the product going to be? And with each of these Birch conditions. And we're going to do a reduction. We're going to make more bonds to hydrogen in the ring in each of these cases. The question is, where will we add the hydrogens? And that depends on whether the branch that we have on the molecule is electron withdrawing or electron donating. This is an alkyl group, so it's going to be electron donating through hyperconjugation. If it's electron donating, then you'll never form that lone pair there, because it would be extra unstable if this is adding electrons in. You'll always form the lone pair right next door, and remember that lone pair turns into the extra hydrogen, and so you get the pi bonds there and the hydrogens on opposite sides. So that's your product for that Birch reduction. For this next one, doing the Birch reduction, the sodium is creating the radicals, the methanol adds the hydrogen, the extra hydrogens we're adding on, and the ammonia activates the metal. So in this case we have two alkyl groups, and they're both electron donating through hyperconjugation. Both of them have this sp3 hybridized carbon that's going to bleed into one of the pi bonds in the ring. So these are both electron donating. And what that means is you will never form that first lone pair on the carbon that the isopropyl group is connected to. You'll never form that first lone pair on the carbon that the methyl group is attached to, because in both of those cases, they would be adding electrons to that carbon, and that would destabilize the lone pair. The lone pair will always form, excuse me, the lone pair will form more often at the carbon next door to one of those. And so you would get it there, for example, or there. And in either, and remember those lone pairs turn into the extra hydrogens. So those are the carbons where you'll have the two hydrogens. And next door, you'll have the pi bonds. Excuse me. And so that's the product you'd get for that, for that reaction. Excuse me. Okay, if we do this next one, we're looking for the branches, whether they are electron donating or electron withdrawing. Here we have alkyl branches, so they're both going to be electron donating, which means the lone pair will never form here. The lone pair will never form there. Both of those carbons are receiving electrons from the alkyl groups. It'll always form next door. And so it would form here and here. Well, it could form, it'd form in between them. Notice that it wouldn't form on the opposite ends, right? You wouldn't have it form here, because then you'd eventually have the radical, the radical on the opposite side. And that radical would later be destabilized because the alkyl group is also donating electrons there. So it wouldn't form there, and for the same reason it wouldn't form para to the isopropyl group, because later in the mechanism you'd have a radical attached to the isopropyl group carbon, and that would be destabilized by the electrons being donated by that sp3 carbon in the isopropyl group through hyperconjugation. So the only two carbons the only position where you can have the lone pair and then later the radical, and they're not attached to the carbon rings, is in these two here. Those are the places where you form those negative intermediates. That's where the hydrogens ultimately go. And so the pi bonds end up going on either side. And so far by coincidence, they've always been going vertical on the opposite two sides. That's not always going to be the case. You can't just learn that. You would always have to look at the branches. So here, for example, you'll draw the molecule and ask yourself, first, are these electron donating or electron withdrawing? They're alkyl groups, so they're going to be electron donating through hyperconjugation. That means that neither the lone pair nor the radical could ever form at either of those positions. So the only positions that are available then for the lone pair or the radical are these opposite ends there. Because if you form the first lone pair here, you'll form the radical on the isopropyl carbon later, which would be destabilized by hyperconjugation. And if you form the lone pair there originally, you'll form the radical on the opposite side, and that would be destabilized by hyperconjugation. So the most stable, and therefore the major product that you would get, is with the lone pair and the radical where we've drawn them here. And remember, those ultimately turn into bonds to the extra hydrogen, which means that the pi bonds form on the side. For E, what we have is a branch. Ask yourself, is it an electron donating or an electron withdrawing group? Now in this case, this is not an alkyl group. This has really electronegative atoms in it. Those are going to pull electrons out of the ring, which means if the lone pair forms there, it'll be really stable. So that's where the lone pair is going to form. And then you have the radical on the opposite side. Those turn into the hydrogen. Those attack the hydrogen on the methanol and turn into the extra hydrogen that you have. And so the pi bonds would go here. This next one has a couple branches. Now we have one branch that is electron withdrawing. A lot of electronegative group atoms there, so the electrons are going to be sucked away from the carbon that's attached to. The isopropyl group is electron donating. So that's going to add electrons to that carbon. So we know that the lone pair definitely is not going to form there. So we're not going to add our hydrogen there. And the most stable place for the lone pair to form would be next to the electron withdrawing group, because then the lone pair and the charge that comes with it would be stabilized by being spread out over more atoms. So it definitely forms there, which means that's where the hydrogen is going to go. The radical would form on the opposite side, and so you'd get the other extra hydrogen there, and so the pi bonds would have to be right there. And so that would be your product for that Birch reduction. So hopefully that gave you a little clarity on what the Birch reduction is and why you get these patterns, why it happens and why you get these patterns when you have branches on the benzene ring. Electron donating branches on the one hand, like alkyl groups, or electron withdrawing branches on the other hand, things that have a lot of